In a previous lesson, we saw that the harmonic series diverges. Essentially, we saw that the sum from k equals 1 to infinity of 1 over k is not finite, it diverges. But what about the sum from k equals 1 to infinity of 1 over k squared? In a previous lesson, it appeared that this sum was starting to converge to a finite number when we looked at the sequence of partial sums, but we could not prove that it converged. Also, what about the sum from k equals 1 to infinity of 1 over the square root of k? Does that series converge? So what we're getting at is we want to ask a general question: for what values of p does sum from k equals 1 to infinity of 1 over k to the p converge? It appears that for p equals 1 that it diverges, and for p equals 2 that it converges. What about all the other values of p? Well, these are actually called p series. And we're trying to ask the question whether these p series converge or diverge. And the way that we're going to answer this question in this lesson is that we're going to use what is called the comparison test. The comparison test is going to compare the sizes of two different series, and then we're going to use what we know about one of the series to say whether the other series diverges or converges. So we're going to let a sub k and b sub k be sequences of positive numbers, sequences of positive terms, and we're going to say that a sub k is less than or equal to b sub k for all k greater than or equal to some capital K. So what I'm imagining here to draw in this scenario is that I have a sequence. I'm going to call this sequence a sub k. Looks like that. And then I'm going to have another sequence, b sub k, that looks like this, where it starts maybe even underneath a sub k, but in fact ends up above a sub k for the rest of time. So the idea is that a sub k does not have to be smaller everywhere, but it does have to be smaller than b sub k for the tail end of that sequence. Now, if b sub k, which is the larger sequence or series in the tail, converges, then we say that a sub k converges. So if the larger series converges, or at least larger in the tail of the series, then the smaller one converges. But if the smaller one diverges, if the sum from k equals 1 to infinity of a sub k diverges, then the larger one must diverge. Now, what we'd like to do is to prove this test to you. And like we did previously, we're going to prove this by appealing to the definition of series convergence. Okay, so for the beginning of this proof, I want to assume that a sub k is less than or equal to b sub k for all k. And I'm going to prove this just saying for all k greater than or equal to 0. But the same proof is going to work if I say for all k greater than or equal to some capital K. Then I want to define my sequences of partial sums. A sub n is going to be the sum from k equals 1 to n of little a sub k. And b sub n is going to be the sum from k equals 1 to n of little b sub k. So these are the sequences of partial sums. Now, since the terms are both positive, we can say that A sub n and B sub n, the sequences of partial sums, are increasing sequences. So here what we're seeing is that because the terms are positive and A sub n and B sub n are sequences of partial sums, then each term for A sub n or B sub n is going to be greater than the term before it. So these sequences are strictly increasing. They are monotonic. And we can say that the sequence of partial sums for A sub n is less than or equal to the sequence of partial sums for B sub n for all n. Now, those facts are going to be true whether we prove A or B. So first I'm going to prove A. So if B sub n converges, okay, then we can say that the limit as n goes to infinity of B sub n is equal to B. And because B sub n is an increasing sequence, we can say that B sub n is less than or equal to B for all n. Okay, so not only does this sequence of partial sums converge, but it converges to a number that is larger than all of the partial sums. Okay, so then we can say that A sub n, the sequence of partial sums for the A sub k series, is less than or equal to B sub n, but that's also less than or equal to B. And A sub n, we already know, is monotonic. So what we have is that A sub n, my sequence of partial sums, is monotonic, it's increasing, but it's also bounded. So we can use a previous theorem that says, therefore, A sub n must converge. We have an increasing bounded sequence, and so A sub n converges. So that tells me that the series sum from k equals 1 to n of A sub k must also converge. So we want to use similar arguments here for the next part. Okay, we want to say if A sub n diverges, okay, then we can say that the limit as n goes to infinity of A sub n is in fact infinity. Now, not all divergent sequences have to go to infinity, but because A sub n is a sequence of partial sums that is increasing, it must diverge to infinity. So this is since A sub n is increasing. Okay, well, since B sub n is greater than or equal to A sub n for all n, then it must be that the limit of that sequence of partial sums is also infinite. And therefore, if the sum of from k equals 1 to infinity of A sub k diverges, then the sum from k equals 1 to infinity of B sub k must also diverge. And now that we have this comparison test, we're going to try to use series that we've already shown converge to help us determine other p-series in particular that converge.